Hey everyone, welcome to this full paper walkthrough for ENGAA 2019 Section 2. It's a bit more complicated in Section 1A and 1B. You get 20 questions and you have an hour to do them. So yeah, let's get straight into it. So question 1 is a pretty standard refraction question, and you want to be using the equation n1 sine theta 1 is n2 sine theta 2. So you're given the first scenario when x is 60 degrees and y is 45 degrees, and you can plug these values into the equation using n1 as 1 because the ray is coming from a vacuum into the medium, and you end up with n2 being root 3 over root 2. You can then plug in the second scenario when x is 45 degrees to work out that sine y in this situation is 1 over root 3, which is A. Question 2 is trying to test how well you can deal with resistor networks. So for x, the total resistance is 2R because the resistors are in series. For y, you have R in series with a parallel combination of R over 2, giving 3R over 2 in total. And for z, you have 2R on the top and R on the bottom, giving 2R over 3. Now, because each arrangement of resistors is connected across the same battery, you want to use the equation power equals V squared over R to obtain the relationship that power is directly proportional to 1 over R, which means the higher the resistance, the lower the power. If you then want to order the arrangements when placed in order of increasing power, the one with the lowest power will be the one with the highest resistance, which is X, followed by Y, and then Z will have the highest power because it has the lowest resistance. Question 3 is a pretty straightforward police question. You're told that the load moves downwards at a constant speed, which means that the block must also move at a constant speed, which means that the resultant force acting on the block is 0. You can then resolve forces on the block parallel to the slope. So tension is equal to 5 plus the component of the block's weight acting down the slope, which is equal to 2g sine 30. So tension is 15. And the tension is the same across the string because the pulley is smooth. So now moving over to the load, you can also see that tension is equal to mg, where m is the mass of the load. So 15 is equal to 10m, which means m is 1.5 kg. Question 4 is pretty much a potential divider question. So when the switch is open, the overall resistance is 8 plus 3 plus 1, which is 12. So the voltage across the 3 ohm resistor is 3 over 12 times the total voltage, 16, which gives you 4 volts. When the switch is closed, you now have 8 ohms in parallel with another 8 ohms, which gives you a total parallel resistance of 4 ohms. So the voltage across the 3 ohm resistor is 3 over 3 plus 4 plus 1, which is 3 over 8 times 16, which gives you 6 volts. For question 5, you're told that the distance between adjacent nodes in the wave is 4 centimeters. And by looking at the diagram, you can see that 4 centimeters is equal to half of the wavelength. So the wavelength is 8 centimeters. You can then use the equation V equals F lambda to work out the frequency of the wave, which is 3.2 over 0.08, which gives you 40 hertz. The total distance traveled by a particle is equal to 4 times the amplitude, because in one cycle it goes up, back to the equilibrium position, down, and then back to the equilibrium position again, times 2, because there are 2 waves, times 40 cycles per second, 40 hertz, times a time interval of a minute, which is 60 seconds, and when you work that out, it comes out to 288 meters. For these types of questions, it's always useful to draw a diagram. So you're told that the ray strikes the boundary between the block and the air at an angle theta to the boundary, which means the angle to the normal is 90 minus theta. So when you plug this into the equation n1 sine theta 1 equals n2 sine theta 2, where theta 1 is 90 minus theta and theta 2 is 90 for total internal reflection, you end up with nb for the block times cos theta equals n air. You know, for the block, NB is equal to C over V block, and V block is the velocity of light in the block, which is F times lambda block. And for N air is equal to C over V air. So you can then use this relationship as well as the one above, that NB cos theta is equal to N air, to obtain lambda block as V air times cos 65 over the frequency. So the average pressure on the ground under the pyramid is equal to the weight of the pyramid divided by the area that it acts on plus atmospheric pressure, When you're calculating the weight of the pyramid and dividing it by the area, the two areas cancel out, so you don't need to worry about the lengths of the square base. And when you cancel out the common factors, you end up with the pressure being 140 times 7 plus 100 from the atmospheric pressure, which is 1080 kilopascals. For question 8, you're told that the pressure is directly proportional to the density. So you can write this as P is equal to K times rho, where K is the constant of proportionality. You then want to be using the equation PV equals constant to obtain a relationship between the pressures and the volumes at a depth h and at a depth x, bearing in mind that the pressure also includes the atmospheric pressure P. So you can write out PV equals constant for both depths and rearrange the equation to obtain the radius r at a depth x as equal to P plus rho gh over P plus rho gx to the power of a third times the radius capital R at a depth h, which is c. Question 9 is a straightforward conservation of energy question where the Ke and Gp of the block is equal to the work done by friction to bring the block to a stop. So the Ke is equal to half times 2 times 8 squared, and the change in Gpe is m, which is equal to 2 times gravity g times the change in height, which is 4 sine 30, because it travels 4 meters down the slope, and the slope is at an angle 30 degrees to the horizontal. This is equal to the frictional force times 4, because work done is force times distance. You can then rearrange this and simplify it to obtain the frictional force as 26. So question 10 is a moments question, and you can first work out the weight of the beam by resolving forces vertically upwards. You know that the contact force at the pivot is 800 and the reaction at P is 0.6x. So 800 plus 0.6x is equal to weight of the beam x. And you can rearrange this to obtain x as 2000 newtons. You then want to work out the distance of the center of gravity of the beam from the pivot, and you can take moments about the end q, calling the unknown distance between the pivot and the center of mass of the beam g as z, to obtain z as 1.8 meters. So question 11 is actually a surprisingly difficult question. You can write the speed at the start of the third second as u, and using the equation s is ut plus half at squared, you can obtain an expression in terms of u and a for the distance traveled in the third second. At the start of the fourth second, you can write the speed as v, and using a similar sort of calculation from the previous one, you can obtain an expression in terms of v and a for the distance traveled in the fourth second. You can then use the equation v equals u plus at to obtain a relationship in terms of u and a for v. And you can plug this into the expression 14.4 is equal to v plus half a to get two relationships in terms of u and a. And then you can solve these simultaneously to obtain the acceleration as 2.2. A is 2.2, and you can work out u as 11.1 using 12.2 is equal to u plus half a. So you can then use these two values to work out the velocity at the sign as 11.1 minus 2 times the acceleration, which gives you 6.7 meters per second, which is c. For question 12, you have the value of the spring constant and the maximum strain energy in the spring, and you can use the relationship energy is equal to half kx squared to work out the extension of the spring as 0.1 meters. You can then use F is equal to kx to work out the force in the spring at its maximum value as 5 newtons. Now, the force increases at a constant rate of 0.2 newtons per second, so to get to 5 newtons, it takes 25 seconds. The power is then just the energy stored in the spring at when the force is at its maximum value divided by the time taken to get to that maximum value, which gives you 0.01 watts. For this question, you're told that the resistances and the voltages are identical. So you can write the voltage of one cell as V and the resistance of one resistor as R to obtain that when the switch is open, the total voltage is 2V and the total resistance is 3R. This means that the current is 2V over 3R and power is I squared R, which is equal to 4V squared over 9R. When the switch is closed, the current always follows the path of the least resistance. So it will bypass the cell that's in series with the resistor. So now the total voltage is V and the total resistance is 2R. This means that the current is V over 2R and the power is now V squared over 4R. The new power is now 9/16 of the original power, so the answer is B. So for question 14, you can get the extension of the bar by focusing only on the forces on the caravan. So for the caravan, the tension in the bar minus the resistive force D2 is equal to MA. So T bar is equal to MA plus D2. Now the extension of the bar is equal to FL over AE, where E is the Young modulus. And you can obtain this relationship by rearranging the equation for Young's modulus, which is stress over strain. You can now plug in the force in the bar, which is equal to T bar, which is equal to MA plus D2, to obtain X as MA plus D2 times the length over E times A, which is C. So for this question, you basically want to apply the potential divider equation to all three cases. So you know initially that the voltage across the battery you can write as V. So the current voltmeter reading is 2V over 3 minus V over 3, which gives you V over 3. You're applying the potential divider equation to both the top branch and the bottom branch. For case 1, if you add T in parallel with P, this would cause the parallel combination of P and T to have a lower overall resistance than P by itself. So the potential just after P would decrease, while the potential just after R would remain the same, causing the voltmeter reading to increase. The same thing would happen if you added T in series with Q. The potential just after P would decrease, because now Q and T take up a larger voltage across that branch, which would also cause the voltmeter reading to increase. If you instead added T in parallel with R, this would cause the parallel combination of R and T to have a lower overall resistance than R by itself, which would cause the potential just after R to be lower than what it was originally, and the voltmeter reading would fall. So to cause an increase in the magnitude of the voltmeter reading, you want either case 1 or case 2. So for these types of questions, you want to basically be going through each of the statements one by one. So looking at the first statement, the magnitude of the acceleration is only equal to the magnitude of acceleration of free fall when it's at its highest point. Now this is true because at the top, air resistance is 0, so the only force acting on the ball is its weight. So the acceleration is equal to the acceleration of free fall. The second statement, that the time taken for both the upward and downward journeys is the same, is incorrect, and you can see this just by looking at the graph. And the third statement, that the maximum increase in GP of the ball is less than its initial KE and greater than its KE when it returns to the starting position, is true, because air resistance is acting on the ball, which causes some dissipation of energy. So the answer is F. Question 17 is a projectile motion question, so you always want to start off by drawing a clear diagram. You're told that the stone is projected at an angle 30 degrees to the horizontal, so the vertical component of the velocity is u sine 30, where u is the initial velocity, which is equal to u over 2. You can then use v equals u plus at vertically, because you know that the vertical speed at the top of the parabola is 0, to work out u as 12 meters per second. You then want to work out the height when the time is equal to 1 second, and you can just use the equation s is equal to ut plus half at squared to obtain the height as 1 meter, which is 8. Question 18 is genuinely a hard question, probably one of the toughest ENGAA questions I've ever done. But you want to go about approaching it the same way you'd approach any other moments question. So you want to take moments about the hinge. So you start off with the angle between the ramp and the vertical being theta, and you can write the angle between the ramp and the cable as alpha, and then you can take moments about the hinge to get W, which is the weight of the ramp, times L over 2 cos 90 minus theta is equal to T sine alpha times L. Because the vertical between the hinge and the winch and the length of the ramp are the same, you basically have an isosceles triangle. So you can obtain a relationship for theta in terms of alpha. So alpha is 180 minus theta all over 2, which is equal to 90 minus theta over 2. And you can then plug this back into the Mohm's equation and rearrange to get that the maximum tension in the cable is, well, the tension in the cable is W sine theta over 2. And you get the maximum tension when theta is equal to 90 degrees. So T is equal to W sine 45. And the maximum tension is therefore W root 2 over 2, which is W over root 2. So for question 19, the initial kinetic energy of the particle of mass m is big E. And you can write big E as equal to half mv squared, giving v is root 2e over m. You can then plug this into the equation for conservation of momentum, writing x as the velocity of the coalesced particles after they collide. And you can then obtain an expression for x in terms of m, big M, and e, where x is m root 2e over big M over m plus big M. You can then plug this into the expression for the kinetic energy after the collision, and you get me over m plus big M. And you can subtract this from the initial kinetic energy E to give the total KE transferred to other forms, which turns out to be big M times E over big M plus M, which is B. So for question 20, last question on the test, you want to work through each of the cases X and Y separately. So for case X, you'd use the equation n1 sine theta 1 equals n2 sine theta 2 to work out the refractive index of medium X as root 2. And the same sort of thing for case Y, n1 sine theta 1 equals n2 sine theta 2 to work out the refractive index for medium Y as 2 over root 3. Now root 2 is approximately 1.41 and 2 over root 3 is approximately 2 divided by 1.8, which is approximately 1.1. So for a wave traveling between mediums X and Y, for total internal reflection to occur, it must be traveling from a medium of higher refractive index to a medium of lower refractive index. So it must be going from X to Y. Now you can then use the same equation n1 sine theta 1 equals n2 sine theta 2 to work out that the angle for total internal reflection, sine of that angle is 2 over root 6. Now 2 over root 6 is greater than root 2 over 2, but it's less than root 3 over 2. So it's greater than sine of 45, but less than sine of 60. So the critical angle must be between 45 and 60, giving your answer as C. Thank you for watching, everyone. Hope you found it useful. And for more ESAT practice and preparation resources, make sure to check out our website. Link will be in the description.